How do you keep track of 500,000 pairs of the world's most expensive, highly coveted shoes without losing your mind, bankrupting your company, or surrendering your soul to the relentless, chaotic void of a massive industrial warehouse? This is Critical Path, where we explore stories and innovations about our global supply chain that connect our world to your everyday life. Imagine, if you will, standing in a massive, modern cavern of consumer desires. The air smells faintly of premium leather, vulcanized rubber, and the distinct scent of internet hype. This is not just any ordinary storage facility. It is a meticulously guarded vault located in Hillsborough, New Jersey. Inside, resting on miles and miles of high-density racking, are roughly 500,000 pairs of the world's most sought-after athletic footwear. We are talking about the holy grail of sneakers, managed on a consignment basis for a company called Stadium Goods. Welcome to the secondary market paradise. The global sneaker resale ecosystem is an absolute behemoth, currently valued anywhere between $6 billion and an estimated $30 billion. In this world, a single pair of shoes is not just something you wear to the gym to avoid eye contact with your neighbors. It is a tradable, volatile financial asset. Individual pairs sitting on these shelves routinely command price tags ranging from a modest $50 to an eye-watering $15,000 or more. Now, I want you to imagine the high-stakes operational nightmare at the absolute center of this financial goldmine. Because Stadium Goods operates on a consignment model, the company does not technically own the merchandise lining its shelves. Instead, everyday resellers, people like you, me, or a 16-year-old named Tyler who has a suspiciously fast internet connection, ship their prized footwear to the intake centers. There, experts put each item through a rigorous 10-step authentication process before the shoe ever sees the light of a storage bay. Once those authenticated shoes are stored, the third-party logistics provider, Barrett Distribution Centers, assumes total financial liability for every single stitch, lace, and rubber sole. The core problem here is that in a colossal, heavily packed facility, human eyes and traditional inventory methods are remarkably tragically fallible. In the past, Stadium Goods struggled with a legacy warehouse provider that was plagued by an unacceptable shrink margin of 1.5% to 2.5%. And look, a 1.5% error rate might sound perfectly fine if you are guessing the weight of a pumpkin at a county fair. But when an inventory item is valued at thousands of dollars, a misplaced shoebox is not merely a minor bookkeeping error. It is functionally identical to throwing pure, unadulterated cash directly into an industrial shredder. If a customer goes online and buys a specific, ultra-rare size 9.5 sneaker, and the warehouse associate cannot locate that exact physical box among 500,000 identical-looking parcels, the entire system breaks down. The sale collapses, the buyer leaves to complain on the internet, and Stadium Goods is left on the hook to reimburse the original consignor for the full market value of the lost asset. To make matters even more uniquely chaotic, sneaker trends move at the absolute speed of internet hype. Inventory at Stadium Goods typically turns over at least once per quarter. That means goods are constantly being received, sorted, stored, picked, and shipped in an endless, high-speed game of logistical musical chairs. Under the old, manual counting regime, tracking this frantic game was a massive financial sinkhole. Operations managers had to pay teams of inventory specialists to ride through the air on massive, slow-moving cherry pickers, craning their necks to manually scan barcodes on top-tier shelves. This tedious, mind-numbing physical process cost the facility an estimated $300,000 per year in labor, maintenance, and training, yet it still failed to produce flawless records. Clearly, traditional logistics had hit a brick wall. To manage a literal sea of 500,000 hyper-specific collector shoes without drowning in operational costs and inaccurate records, the operations team needed a seemingly impossible solution. They needed a system that could see through the dark, reach heights of 30 feet without a ladder, and count thousands of individual packages in the blink of an eye without interrupting the daily hustle of a busy fulfillment center. To truly appreciate the sheer genius of the mechanical solution that was eventually deployed, we must first descend into the logistical purgatory known as manual cycle counting. Inventory control in a high-density, multi-client warehouse is traditionally about as much fun as watching paint dry on a counterfeit sneaker. Under the manual paradigm, maintaining accuracy in 34 massive aisles of very narrow aisle selective racking required brute force human labor. A single inventory control specialist would strap into a heavy cherry picker or an order picker truck, ascend several stories into the air, and proceed bay by bay, shelf by shelf, scanning individual labels with a handheld radio frequency gun. Because human fatigue is an inescapable reality, individuals performing these highly repetitive tasks for hours on end naturally make mistakes. They miss labels, they accidentally double scan items, or they enter incorrect digits into the system because their eyes are crossing from boredom. Moreover, executing these massive facility audits historically required logistics managers to halt standard operations entirely. You simply cannot have massive material handling equipment zipping around the narrow aisles to pull customer orders, while simultaneously sending teams of slow-moving counters up into the same exact tight spaces. Consequently, full facility counts often stretched over days or entire weekends, driving up overtime labor expenses and delaying outbound customer shipments. Let us look at the raw economics of this traditional nightmare. The estimated annual counting labor cost was up to $300,000 per facility. The average financial cost per individual scan was approximately $1.50. And remember that margin of error, the shrink? A 1.5% to 2.5% variance. The required equipment was a fleet of scissor lifts, cherry pickers, and handheld scanners. When inventory accuracy falls below an acceptable threshold, which is typically around 95%, many industrial facilities are forced to trigger emergency full facility physical counts. These are the dreaded logistics fire drills, where normal factory or warehouse operations grind to a complete and utter halt, and every available staff member is handed a clipboard or a scanner to search for missing merchandise. In high-velocity environments, a missing pallet or a misplaced shoebox can trigger hours of wasted labor as workers comb through rows of products desperately trying to reconcile physical reality with what the digital database claims is on hand. Beyond the raw financial drain, the psychological toll on warehouse staff was immense. Nobody enjoys being blamed for a phantom missing box, and searching aimlessly through 500,000 identical-looking parcels is an exercise in pure frustration. Therefore, the push to find a digital savior was not just about protecting the bottom line, it was about saving the sanity of the workforce and creating a frictionless fulfillment machine. To banish the clipboards and cherry pickers to the relics of logistics history, Barrett Distribution Centers turned to a Pittsburgh-based company born out of the Autonomous Flight Research Labs at Carnegie Mellon University. The company is called Gather AI. The solution they proposed sounded like pure science fiction to traditional warehouse operators. Instead of sending humans to find the shoes, they would unleash a fleet of fully autonomous aerial drones to fly up and down the narrow aisles, surveying the inventory with advanced computer vision. Now, at first glance, utilizing drones inside a warehouse sounds like a spectacular recipe for absolute disaster. One might instantly imagine thousands of dollars in rare sneakers being chopped to bits by rogue plastic propellers, or drones losing their electronic minds and crashing violently into industrial steel beams. Outdoor drones, like the ones used for leisure photography, aerial surveying, or mapping agricultural fields, rely heavily on global positioning system satellite signals and magnetic compasses to figure out where they are in three-dimensional space. However, step inside a massive steel and concrete warehouse, and standard GPS ceases to function entirely. The thick metal roofing blocks satellite communication, and the dense network of massive steel storage racks creates chaotic magnetic interference that would render a standard compass virtually useless. To operate safely in complex indoor environments, these drones absolutely cannot rely on external satellite signals. So how does a flying robot know that it is hovering exactly in front of Bay 12, Level 4, and not about to paint the concrete wall with its own electronic components? The answer lies in a highly sophisticated, yet elegantly simple combination of passive localization and computer vision. Instead of forcing warehouses to spend millions of dollars installing expensive, powered active radio beacons or complex laser mapping infrastructure throughout the facility, the Gather AI system relies on what are known as fiducial markers. Specifically, the team places small, printed square tags known as Aruco markers directly onto the existing physical racking of the warehouse. Aruco markers are essentially high-contrast, synthetic two-dimensional black and white grids that look like simplified QR codes. Each printed Aruco beacon contains a mathematically unique identifier code that can be read instantly by the drone's high-resolution cameras. As the drone takes off autonomously from its charging cart, its onboard cameras continuously scan the environment. The exact moment it detects an Aruco marker on a rack, sophisticated machine learning algorithms calculate the vertical and horizontal pixel coordinates of the marker's center. Because the exact real-world dimensions and positions of the markers are pre-mapped into the drone's digital brain, the software can use the visual size and distortion of the marker to calculate the drone's exact distance, angle, and altitude with a jaw-dropping half-centimeter accuracy across 6 degrees of freedom. By continuously reading these simple paper stickers scattered across the facility, the drone maintains a perfect awareness of its location, executing its flight path with military precision. The drone moves from bin location to bin location, acting effectively as a highly flexible, three-dimensional hovering camera. It can drop low to look at floor pallets, or elevate high into the rafters to inspect top tiers, without requiring a human to ever leave the solid ground. To make the process even more streamlined, the system is designed to be purely software first. This means that instead of manufacturing incredibly expensive, highly specialized custom drones, the system leverages widely available, interchangeable commercial, off-the-shelf drones, such as those made by DJI. By offloading the pure engineering of flight to proven mass-market drone hardware, the developers were able to focus all their intellectual resources on building the incredible software brain that interprets visual data. Once a drone is safely positioned in front of a storage bay, the true magic of the system begins. Traditional inventory clerks armed with handheld scanners can only read a single barcode at a time. They have to aim the laser, wait for the beep, record the entry, and physically move their arm to the next box. Autonomous inventory drones do away with this slow, sequential plodding entirely, by shifting from manual laser scanning to batch computer vision scanning. As the drone hovers in front of a location containing several packages of sneakers, its high-resolution camera takes a single, comprehensive photo containing all visible labels and boxes. The system then utilizes camera-based imaging, combined with real-time data processing algorithms. An exploration of how multi-barcode scanning works reveals a highly optimized, multi-step digital pipeline. First is image capture. The high-resolution camera takes a single, highly detailed photo containing all the visible barcodes, labels, and text in the target area. Second is pre-processing. Warehouses are notoriously poorly lit, with harsh fluorescent overheads casting deep shadows inside narrow aisles. The system automatically enhances the image, using exposure balance, focus adjustment, and high dynamic range filters to make the picture as clear as mathematically possible. Third is detection. Advanced deep learning object detection algorithms, such as YOLO version 8, rapidly scan the frame to find the exact pixel boundaries of every one-dimensional and two-dimensional barcode, no matter how tilted or oriented they may be in three-dimensional space. Fourth is decoding. Each isolated barcode is read simultaneously through computer vision, instantly converting physical lines or grid symbols into usable digital data strings. Finally, data transfer. The resulting decoded inventory records are instantly compared directly against the facility's master warehouse management system to verify that physical reality perfectly matches the digital record. Because the computer's digital brain can detect and decode dozens of labels in a single image frame, the execution speed is mind-boggling. When Stadium Goods and Barrett Distribution Centers transitioned to this method, they managed to reduce the time required to count an entire storage location from several minutes down to an impossibly fast 4.7 seconds. Let the sheer weight of that number sink in. A human worker climbing a ladder or operating heavy machinery to manually read each individual box label might take several minutes to verify a full shelf. The drone flies by, snaps a picture, processes the entire visual field in less time than it takes to tie a pair of shoelaces, and casually moves on to the next task. The drone does not need to pause, aim, or squint. In fact, a single operator can comfortably manage a fleet of up to 3 drones flying simultaneously in different aisles. While one drone is collecting data, the operator can launch a second, and then a third, effectively scaling the facility's inventory capture capacity to a blistering 900 locations per hour. This massive leap in data acquisition throughput means that a full facility inventory audit that once took human counters several days or even weeks to complete can now be wrapped up in a matter of hours. Because the flights can be executed autonomously during employee break times or at the tail end of shifts, when order-picking traffic naturally slows down, the warehouse can maintain continuous, near-perfect inventory awareness without ever actually interrupting the daily flow of business. As we talk through the mechanics of this incredibly high-tech process, it is remarkably easy to form a specific mental picture of how these drones operate. Most people instinctively assume that these flying robots are incredibly complex mobile supercomputers. Observers naturally imagine that the drone's onboard processors are actively reading the barcodes in real time, calculating supply chain analytics as they fly, and making high-level cognitive decisions while hovering in the air. Here is the massive, perspective-shifting revelation that completely blows the standard human assumption out of the water. The drone is not actually reading the barcodes while it flies. In fact, in terms of pure computational intelligence, the drone is functionally a dumb flying camera, executing a massive, high-speed photography session. The drone does not know what it is looking at. It does not know the difference between a high-value, $10,000 Air Jordan and an empty cardboard slot. It has no idea whether a barcode is valid, smudged, or missing entirely. Its only job is to execute a flawlessly precise, pre-programmed flight path, take incredibly high-resolution photos of the shelves, and log those photos locally on its internal storage drive. The actual artificial intelligence magic, the true cognitive heavy lifting, happens entirely after the drone lands. Once the drone completes its autonomous mission and returns to its cart, or when it establishes a solid connection to the facility's local Wi-Fi, the massive batch of high-resolution images is uploaded directly into a centralized cloud-based neural network. It is here, in a remote server farm miles away from the physical sneakers, that the true AI brain takes over. The powerful machine learning algorithms process the millions of pixels captured by the drone's flight. The system creates a real-time digital twin of the physical warehouse environment, recreating the entire facility virtually. Only then does the computer vision software actively go to work, reading the barcodes from the photos, identifying text, and comparing what it visually detects against the digital master logs of the warehouse management system. This counterintuitive operational design is brilliant because it neatly solves the massive engineering problem of power and weight. If engineers tried to pack a heavy, heat-spewing supercomputer and massive graphics processing units onto a small aerial drone to analyze computer vision data in real time, the drone would become too heavy to fly efficiently, and its battery would drain in a matter of minutes. By turning the drone into a lightweight, hovering paparazzi that simply captures visual data to be decoded later in the cloud, operations can leverage off-the-shelf, cost-effective consumer drone hardware while retaining access to the unlimited processing power of modern cloud computing. In a perfect theoretical world, every shoebox would be perfectly aligned, every barcode would be printed with pristine precision, and lighting would always be flawless. Of course, anyone who has ever stepped foot inside an active commercial logistics center knows that the real world is messy, chaotic, and decidedly non-perfect. Boxes move on conveyor systems, get handled by delivery drivers, and slide in and out of tight metal storage racks. In the process, labels get scratched, smudged, torn, or partially obscured by clear industrial shrink wrap. Furthermore, operations frequently rely on human-written notes scrawled on the sides of boxes to denote expiration dates, batch numbers, or special handling instructions. If automated inventory relied purely on rigid, old-school barcode readers, a single scuffed label, or a piece of reflective plastic wrap would cause the whole system to fail. This is where advanced physical artificial intelligence distinguishes itself from standard digital automation. The computer vision platform has been trained on millions of real-world images of pallets, cases, and labels. Because the machine learning algorithms have seen virtually every variation of label degradation imaginable, the system delivers best-in-class precision and recall, capable of deciphering codes that a human eye might struggle to read. An analysis of these specialized optical capabilities reveals that the technology goes far beyond simple line-by-line reading. First, there is obscured and damaged label decoding. Advanced filters and computer vision algorithms can rebuild contrast in faded labels and digitally fill in missing patterns caused by scratches or tears, maintaining reliable data capture even on rough packaging. Second is text recognition, or optical character recognition. The platform features highly advanced technology trained on both printed and handwritten text. Drones can literally read product codes, lot numbers, and expiration dates directly from the physical cardboard, even if no barcode exists for that specific data point. Third is true empty detection. One of the most common issues in a high-density warehouse is ghost inventory, where the database claims a box is in a location, but the shelf is actually physically empty. The AI specifically recognizes negative space, allowing operations to instantly clear out ghost entries in the database and maintain optimal space planning. By giving the system visual intelligence rather than just laser-scanning eyes, logistics operators can maintain a highly robust, fault-tolerant stock-keeping ecosystem. As the artificial intelligence platform matured through continuous exposure to thousands of flights, developers realized that visual data contained far richer information than simply reading numbers off a sticker. In April 2024, the platform rolled out a pair of highly advanced, industry-first capabilities that pushed the boundaries of what automated inventory systems can achieve: inferred case counting and location occupancy. To understand the genius of inferred case counting, consider how warehouse managers traditionally had to handle a partial pallet or a split case. If an associate needs to know exactly how many boxes are left on a high-tier pallet where only the front face is visible, someone traditionally had to take heavy machinery, pull the pallet down to the floor, manually count and restack the boxes, and put it all back up. It is an incredibly labor-intensive and annoying task that actively disrupts workflow. The inferred case count functionality utilizes image-based pattern recognition to estimate the physical volume of packages in a location without ever touching them. As the drone flies past a shelf, its cameras capture a high-resolution photo of the pallet's visible face. The artificial intelligence assesses the geometric patterns in the photo to calculate the maximum number of visible layers of boxes stacked on the pallet. The system then automatically references the master database to pull what is known as T-high data. In supply chain terminology, T-high refers to the standard stacking pattern of a pallet. The number of cartons stored on a single layer, which is the T-high, multiplied by the number of layers high the pallet is stacked, which is the high. By taking the visually detected height from the drone's photo and multiplying it by the known tie metric stored in the database, the AI can reliably infer the total number of cases resting on that pallet. If the inferred physical count does not match the expected count recorded in the master database, the system flags the location as a variance on the web dashboard. Managers can then dispatch a human worker only to the specific locations that actually need physical attention, reducing manual counting labor by an estimated 87% to 90%. Similarly, the location occupancy feature allows the AI to calculate the exact percentage of utilized space within a physical storage slot. By measuring the volume of stored products against the total available volume of the rack, operations managers can identify underutilized areas. This data is used to actively combat a logistics problem known as honeycombing, allowing operators to strategically consolidate identical products into a single location and maximize the overall cube utilization of the facility. A thorough review of the rapidly evolving logistics ecosystem makes it clear that while smart software is the primary driver of value, the actual mechanical wings carrying that software are undergoing a severe evolution. When autonomous drone inventory systems were first rolled out, utilizing off-the-shelf commercial drones, such as those made by Chinese tech giant DJI, made a massive amount of economic sense. These mass-market flying robots are incredibly cheap, widely available, and highly reliable. However, as facilities demand faster speeds, narrower aisles, and the ability to operate in more extreme conditions, the industry is seeing a marked shift toward advanced, American-made, purpose-built logistics drones. Specifically, many operations are starting to integrate platforms like the Starling 2 Logis, developed by Modal AI. A direct comparative analysis of the physical hardware specifications highlights the tangible operational advantages gained by transitioning to next-generation purpose-built robotics platforms. A standard commercial drone has a scan velocity capacity of 300 pallets per hour, while the purpose-built drone hits up to 500 pallets per hour. Total fleet capacity jumps from 900 locations per hour to 1,500 locations per hour. Aisle width tolerance drops from a minimum of 5 feet 4 inches to as narrow as 4 feet 5 inches. And instead of just static obstacle detection, the advanced models feature dynamic obstacle avoidance. The reduction in required aisle width is a massive win for facility directors. Real estate for a massive warehouse is remarkably expensive, and squeezing more storage capacity out of the exact same physical building footprint is the holy grail of logistics. By operating with a purpose-built drone that can safely squeeze through aisles that are over a foot narrower than traditional limits, facilities can narrow their storage racks and dramatically increase their total inventory volume without buying more land. Furthermore, the introduction of dynamic obstacle avoidance means that drones can safely fly through busy, active facilities where human workers and moving material handling equipment are constantly crossing paths. Instead of having to strictly isolate an entire aisle with safety cones or schedule flights exclusively during break times, these advanced aerial platforms can actively sense moving objects in their path and navigate around them dynamically. It is vital to recognize that the flying drones do not operate in a vacuum. Instead, they are merely one highly visible component of a tightly choreographed, end-to-end mechanical ballet that keeps stadium goods running smoothly at the Hillsborough facility. To trace a single pair of sneakers from arrival to customer delivery is to see modern robotics and digital supply chain architecture working in perfect harmony. First is receiving and 10-step authentication. High-end collectible footwear arrives at the dock doors. Stadium Goods employees manually inspect each pair to verify brand legitimacy, condition, and quality, ensuring buyers get exactly what they paid for. Second is automated bagging and labeling. Verified items are placed into a modified auto-bagger system supplied by Sealed Air. The system seals the shoebox in a protective polybag and prints a custom LPN barcode directly onto the plastic exterior. Third is storage placement. Order picker operators load the carton shoes onto carts and transport them into the 34 aisles of very narrow aisle storage. The items are stacked, with their LPN barcodes facing outward toward the aisle, so that they remain perfectly visible to the scanning drone fleet. Fourth is autonomous auditing. Periodic drone flights zip through the storage bays, snapping high-speed batch photos to ensure that reality on the physical shelves perfectly reflects what the master warehouse management system digital record claims is on hand. Fifth is batch picking. When customers place an order on the digital storefront, workers on operator-up trucks are guided by batch pick instructions to efficiently pull the correct polybagged shoes from the racks. Sixth is automated right-sized packaging. The picked orders are dropped at a staging point next to a specialized automated packaging system created by CMC Packaging Automation. This massive machine analyzes the physical dimensions of the polybag, builds a custom-sized corrugated shipping carton perfectly wrapped around the item, weighs the package, and slaps the outbound customer shipping label onto the box. By offloading the slow, repetitive physical work to specialized machines at every possible step, the Hillsborough facility can turn over its entire inventory at blinding speeds while maintaining near-perfect accuracy. While the idea of flying inventory drones through a facility is an absolute game-changer, developers are already looking ahead toward the next massive leap in supply chain visibility. The overarching goal is not merely about building better aerial hardware, it is about perfect, omnipresent digital intelligence. Developers are aggressively working to decouple their core artificial intelligence vision algorithms from aerial robotics entirely. By taking the exact same software brains that read barcodes, analyze occupancy, and recognize text, and applying them to static-mounted cameras, employee wearables, and physical sensors on human-operated forklifts, operations can create a live, real-time digital twin of the entire facility. A digital twin means that management no longer has to wait for a scheduled drone audit flight to figure out where stock is located. Instead, every time a forklift moves a pallet or an employee scans a parcel, the digital recreation of the warehouse updates instantly across the cloud. Furthermore, the introduction of a conversational AI co-pilot feature will allow operations managers to query physical warehouse data using natural language. Rather than pulling massive digital spreadsheets and spending hours trying to cross-reference databases, a director could simply ask the Copilot system, identify any location where high-demand inventory has been misplaced, or show me a list of all consolidation opportunities in aisle 4, and the system will instantly analyze the digital twin to produce an actionable answer. Finally, autonomous inventory technology is moving aggressively into cold storage and industrial freezer environments. In supply chains dealing with pharmaceuticals, high-tech chemicals, or fresh food and beverage items, facilities frequently maintain physical temperatures as low as -20 degrees Fahrenheit. Asking human employees to ride through freezing steel aisles to manually count pallets on paper clipboards is an exercise in pure physical misery. Ruggedized logistics drones engineered to withstand sub-zero temperatures are now taking over these harsh tasks. Flying autonomously through the dark and the cold without complaining about freezing fingers, these robotic systems can audit frozen inventory up to 10 times faster than manual means, ensuring total first-in, first-out compliance to guarantee inventory freshness while keeping human workers comfortably insulated in the control room. To circle back to the terrifying core problem that started this entire narrative journey, maintaining flawless inventory accuracy in a fast-paced consignment model, where missing a single pair of shoes among 500,000 options could cost thousands of dollars, is a massive operational headache. Traditional manual counting strategies were too slow, too expensive, and far too fallible to handle the sheer volume and speed required by a powerhouse like Stadium Goods. By embracing an automated solution driven by Gather AI, Barrett Distribution Centers managed to transition from slow, physical labor to pure, high-speed digital awareness. We have watched paper-thin Aruco markers guide flying drones with sub-centimeter precision in a GPS-denied concrete maze. We have seen advanced object detection models like YOLO version 8 process entire multi-barcode storage shelves simultaneously, yielding a complete location stock check in a mind-boggling 4.7 seconds. But perhaps the most profound mechanism learned is the brilliant, counterintuitive twist of the dumb drone. By resisting the urge to pack heavy supercomputers onto small aerial crafts and treating them instead as lightweight, fluttering paparazzi that capture massive streams of raw visual data to be decoded later in a limitless cloud digital twin, logistics operators have unlocked the true potential of artificial intelligence. At the end of the day, the fusion of robotics and machine learning has done something truly miraculous. It has turned one of the most notoriously chaotic, error-prone environments in modern commerce into a frictionless, hyper-accurate fulfillment machine, where losing your soul is absolutely out of the question. So, here is a question for all of you logistics nerds and sneakerheads out there. If you could deploy a fleet of these computer vision drones to magically organize and catalog any incredibly messy part of your own life, what would you use them for? Let us know down in the comments. Thanks for listening and watching. Please like and subscribe, and make sure to check out our other videos about the global supply chain.